Welcome to Olympiad Math for Year 5. This is Lesson 15, we'll learn Pigeonhole Principle Part 1. In this lesson, we will learn the basic concept and basic usage of the Pigeonhole Principle, and the basic process of solving problems using the Pigeonhole Principle. Let's start with a fun game. Put 3 pigeons into 2 cages. How many ways can we do it? There are only 2 cases as following. Although the ways of placing pigeons are different, one phenomenon always occurs: there is always at least one cage that contains no fewer than 2 pigeons. If we put 4 pigeons into 3 cages, there are 3 ways to do it, but the same phenomenon still holds: there is at least one cage that contains no fewer than 2 pigeons. If we put 5 pigeons into 4 cages, again, there is at least one cage with no fewer than 2 pigeons. Now we have found a pattern: when more than n pigeons are placed into n cages, there must be at least one cage that contains 2 or more pigeons. This is the Pigeonhole Principle. We can see that the essence of the principle is that there are more pigeons than cages. As long as the number of pigeons exceeds the number of cages by 1, there will necessarily be at least one cage containing 2 pigeons. This reasoning can be proved by contradiction: if no cage contained 2 or more pigeons, then each cage could contain at most 1 pigeon, and the total number of pigeons would be at most n, which contradicts the given condition that there are n plus 1 pigeons. The Pigeonhole Principle generally appears in 2 forms, usually called Principle 1 and Principle 2. Principle 1: if n plus 1 pigeons are placed into n cages, then there must be at least one cage containing at least 2 pigeons. Principle 2: if mn plus 1 pigeons are placed into n cages, then there must be at least one cage containing at least m plus 1 pigeons. In the second form, when m equals 1, it becomes the first form, that is, Principle 1 is included in Principle 2. Sometimes we also use these 2 forms in reverse: if there are n cages and we want to ensure that there is at least one cage containing at least m plus 1 pigeons, then we must place at least mn plus 1 pigeons in total. The Pigeonhole Principle is a special way of reasoning. It allows us to make many interesting deductions and judgments. When applying it, we must pay attention to the numbers of pigeons and cages. We often reason from the worst-case scenario, which requires a unique way of thinking. Because of this, the principle is often used to solve relatively complex problems. This lesson focuses on introducing the basic applications of the Pigeonhole Principle. Example 1: Class 5 Spirit Team has 13 members. Mr. Zhang, the math teacher, says, at least 2 people in your team have birthdays in the same month. Do you know why Mr. Zhang can say that? This problem obviously involves months. There are 12 months in a year. Regard these 12 months as 12 cages. Placing the 13 students into the 12 months is then equivalent to putting 13 pigeons into 12 cages. By the Pigeonhole Principle, at least one cage must contain at least 2 pigeons. Therefore at least 2 students have birthdays in the same month. Example 2: there are 43 students in Class 5. How many extracurricular books must the Reading Corner prepare at least, to guarantee that some students can borrow 2 books at the same time? Regard the 43 students as 43 cages. According to the Pigeonhole Principle, to make sure there is at least one cage containing 2 pigeons, the number of pigeons must be greater than the number of cages. Therefore, the Reading Corner must prepare at least 44 extracurricular books. Examples 1 and 2 illustrate the most basic applications of the Pigeonhole Principle. Example 1 is a direct use, while example 2 is a reverse use of the principle. Pay attention: if 5 pigeons are placed into 4 cages, it is certain that at least one cage contains 2 pigeons. However, if 7 pigeons are placed into 4 cages, we can only guarantee that some cages contain 2 pigeons. In the worst case scenario, first place 1 pigeon in each of the 4 cages, then distribute the remaining 3 pigeons one by one into different cages. In this case, the cage with the most pigeons still has only 2. Thus, a modified form of principle 2 can be stated as follows: when mn plus q pigeons are placed into n cages, there must be at least one cage containing m plus 1 pigeons, where q is between 1 and n minus 1, inclusive. Example 3, there are 25 kindergarten children in the oldest class. The teacher distributes 80 candies to them. Show that at least one child received no fewer than 4 candies. Think of placing 80 pigeons into 25 cages. To avoid anyone getting 4 candies, consider the worst case distribution. First, give every child the same number of candies. 80 divided by 25 equals 3 with remainder 5. So each child can receive 3 candies at first. At this point no one has 4 candies. But there are 5 candies left. When those 5 remaining candies are distributed, at least one child must receive 1 more candy and thus have 4 candies. Therefore, at least one child received at least 4 candies. Example 4, 5 guests come to Scarlett's house. She serves them candies. To ensure that at least one guest can eat 6 candies, how many candies must she prepare at least? Treat the 5 guests as 5 cages. We need to guarantee that at least one cage contains 6 pigeons. Consider the worst case situation: if each of the 5 guests eats 5 candies, that requires 25 candies. If we add 1 more candy, it will ensure that at least one guest gets 6 candies. Therefore, she must prepare at least 26 candies. Examples 3 and 4 are direct and reverse applications of Pigeonhole Principle 2. Example 5, when any 3 different integers are chosen, there must be 2 whose sum is even. From the concept of integers, we know that all integers fall into 2 categories, odd and even. Choosing 3 numbers from these 2 categories is like taking 3 pigeons from 2 cages. There must be at least 2 pigeons from the same cage. That means there are at least 2 integers of the same parity, and the sum of 2 numbers with the same parity is even. In the above examples, the number of cages is quite obvious. However, in many cases, the number of cages is not directly given and must be determined flexibly according to the situation. Example 6. Every Thursday the school library is open to Class 5. This Thursday, 38 students from Class 5 went to the library to borrow books. The library has 3 categories: science, literature, and comic books, and each student may borrow any 2 books at a time. Question: how many students at least borrowed the same combination of book types? Regard the 38 students as 38 pigeons. We must decide how many cages there are. That depends on how many different borrowing types are possible when each student borrows 2 books. List the possible types as following. We have our 6 possible types, which are 6 cages. Divide 38 by 6, we have 6 with remainder 2. If we place 6 pigeons in each cage, that uses 36 pigeons, 2 pigeons remain and must go into some cages. Therefore at least one cage contains 7 pigeons. The answer is at least 7 students borrowed the same combination of book types. The main challenge of this problem is correctly creating and counting the cages. Example 7. Every day, 560 people eat lunch at Riverside Primary School. One day at noon, the school cafeteria prepared 4 meat dishes, 3 vegetable dishes, and 2 kinds of soup. Each student took 1 meat dish, 1 vegetable dish, and 1 soup. Question: at least how many students had the same combination of dishes? It is clear that the 560 students can be regarded as 560 pigeons. But how do we determine the number of cages? That depends on how many different meal combinations there are. How many different combinations are possible? According to the multiplication principle, there are 24 different meal combinations. So we can think of this as having 24 cages. Now, from the worst case situation, divide 560 pigeons evenly by 24, we have 23 with remainder 8. That means each cage gets 23 pigeons, with 8 pigeons left over. When those remaining pigeons are placed, some cage must then contain 24 pigeons. Therefore, at least 24 students had exactly the same combination of dishes. When solving problems using the pigeonhole principle, we often need to consider the worst-case situation. Example 8, Ball Drawing Game. There are 10 red, 10 yellow, and 10 green balls of identical appearance mixed together in one cloth bag. Question 1. How many balls must be drawn at least to ensure that 2 balls are of the same color? Question 2. How many balls must be drawn at least to ensure that 2 balls are of different colors? Question 3. How many balls must be drawn at least to ensure that there are 2 pairs of same colored balls of 2 different colors? The given conditions are the same in this problem, but since the questions are different, the answers are also different. The essence of each question lies in the number of cages. In the first question, to ensure that 2 balls are of the same color, consider the worst-case scenario. Draw 1 red, 1 yellow, and 1 green ball first. The number of cages here is 3. Drawing 1 more ball will definitely result in 2 balls of the same color. Therefore, the answer is 4 balls. In the second question, again from the worst-case scenario, suppose the unluckiest situation is that all 10 balls drawn are of the same color, and the requirement of having 2 different colors is still not met. However, if 1 more ball is drawn, it must be of a different color. Here, the number of cages is 10, and the answer is 11 balls. In the third question, start with the worst-case scenario again. If 10 same-colored balls are drawn first, there is only 1 pair of same-colored balls, still not meeting the requirement. At this point, we must draw a pair from the remaining 2 colors. From the worst case again, if we draw 1 yellow and 1 green ball next, the condition is still not satisfied. But if 1 more ball is drawn, it will definitely form a second pair of same-colored balls. Therefore, the answer is 13 balls. This problem applies the pigeonhole principle twice in succession. When using the pigeonhole principle to solve problems, it is crucial to determine what is regarded as the pigeons and what as the cages. The quantities of both must be identified according to the specific context. In many cases, you need to consider the worst-case scenario to ensure the reasoning is both quick and accurate. Here are the practice problems for today. Thank you for watching and hope you enjoy your math today.